The developments are essentially limitless. I just want to give another very quick example to give that impression of how it can be developed, something called the Nadaraya-Watson model. So this is a regression model instead of a classification model, where we want to do kernel regression now. So again, regression is also, we can do linear regression, and so we can use the same rules. And here what we have is that essentially the only difference is that before y was a +1 or -1 label, now y is a value in R. It's a real valued number, and we want to predict a real valued number. So what this model does is very similar to the soft, essentially the same as the soft KNN model from the previous slide. Remember, the soft KNN model declared y0 to be the sign of this function, where these yi's were + or -1. Now y is a real valued number, and we're going to predict a real valued number. So we simply declare our prediction for y0 for an associated x0 to be the weighted average of the labels, or I'm sorry, the weighted average of the responses of all the data that we possess that's weighted according to the kernel function to that data point. So here we're taking a locally weighted average. If we choose the RBF kernel function, we're basically taking a weighted average of our data set of the responses that's weighted according to proximity to the point x0. So another example of this type of a model, which will require some more discussion and is also been developed quite a bit, is called a Gaussian process. We can think of the Gaussian process as a kernelized Bayesian regression model. So before we can define it, we need to see where in the Bayesian linear regression model that we've discussed already, where do the dot products between the data points come into play. Remember, before we can put a kernel of our data into the model, we need to first have dot products between our data points, where we can then justify the kernel by saying we're going to project those dot products, the data, into a higher dimension and then take the dot products. So let's recall the regression setup. We have n observations. We're going to put all of the responses for those n observations in an n-dimensional vector that's in Rn. And then we construct a feature matrix X, where we put the covariates of each data point along the rows of this matrix X. So the ith row of X corresponds to the covariate vector Xi, and the ith dimension of this vector Y corresponds to the response associated with Xi. We then defined the likelihood and the prior in this way. So the likelihood model that we used was we hypothesized that Y is a multivariate Gaussian, where the mean is the product between the feature matrix X with some regression vector W, and then we assumed IID Gaussian noise for Y, and we placed the prior on W that was zero mean Gaussian with some diagonal covariance. We have to now see where dot products come into play, and so let's look at what happens when we integrate out W in this model. What that means is that we want a distribution of Y given X, but not given W, because W has been integrated out in this way, where we multiply the likelihood function that's conditioned on W times the prior on W, and then we integrate out W. We integrate over all values of W to get a marginal likelihood of Y given X. I'm not going to derive this here, but what can be shown, and it's a standard result of working with Gaussians, multivariate Gaussians, is that the result is a multivariate normal that's zero mean, and the covariance is equal to the covariance, the noise covariance, plus this term, which results from the fact that we're integrating out the W here and the fact that we have a mean prior covariance on W there. So we have this term, lambda inverse times the product of the matrix X with the matrix X transpose. So this is a result that we can show. Now notice that we have dot products here. So the value of this matrix, remember X is n by d plus 1. So this matrix product is now n by n. So it's the size of the data. If we have n data points, this is an n by n matrix because y is an n-dimensional vector. The ijth entry in this matrix, by definition of how we made these matrices, is just the dot product between the covariate vector for the ith data point with the covariate vector for the jth data point. So here's where we have our dot products between our data points. They're found and then used to construct this matrix. So now if we take each data point x and we project it into some higher dimensional space according to the function phi, we haven't defined phi yet, we can then say, by following exactly the same setup, where now the ith row of this matrix is phi for xi, put along that row, we then get a matrix that looks like this. Again, it's n by n, so this is an n-dimensional, this is a matrix where I'm using this notation to indicate that we take each row of the matrix X and perform the function phi on it to get a new row. So this is n rows because we have n data points, and then however many columns result from our function phi. It could be infinite dimensional. But then we take the product of that matrix with its transpose, and again we end up with an n by n matrix. So this is still an n by n matrix, where the ijth entry is the dot product between phi of xi with phi of xj, which is the kernel function between xi and xj. So we only need to define a kernel function between all of our data points. And then what we can say is that if we map x to a higher dimensional space using some function phi, that the marginal distribution of y given x and given the mapping, integrating out w, is now a multivariate Gaussian, where all I've done is replace this matrix of dot products between our data points with this matrix of kernel functions between pairs of our data. So this is called a Gaussian process. The Gaussian process comes by integrating out the vector w and then replacing this dot product with a kernel function. So let's notice, before we move on, why this could possibly be useful, at least right off the bat, something obvious about it. So imagine that this function is extremely high dimensional. Maybe it's even infinite dimensional. Then this vector w is infinite dimensional as well, or it could even be a function. There's no chance that we could possibly learn this vector w. We can't even store it in memory. And there's also no chance that we could construct this matrix x, or the function phi of x, because each column would be infinite dimensional. However, if we then use this marginalization fact, where we integrate out w, and it doesn't actually matter that it's infinite dimensional, and that we have an infinite dimensional Gaussian noise prior here, the result is something that we can easily calculate. So we can just calculate the kernel function between all of our data points, and we get a nice n-dimensional multivariate Gaussian distribution where we have a way of actually calculating this covariance, this portion of the covariance k.